Our next sample problem in our solubility section really kind of looks at what we were referring to before as a type 1 equilibrium problem, where we have equilibrium parameters and we need to use those to calculate a K or a KSP value. So I'm going to treat these types of problems the same way we did when we introduced them in chapter 17, which is to write an equation, write an equilibrium expression, make sure all your values are in the right units, and then go forward using an ICE table and solve for your parameters. So again, those are things that you will get partial credit for as we work through quizzes and exams if you're not able to get the correct answer. So always try to have those pieces, and maybe it'll be something that helps walk you through if you're a little bit confused as you start. So first problem tells us lead sulfate, and here it actually gives us the molecular or the empirical formula for it. PbSO4 is a key component in lead acid car batteries. Its solubility in water at 25 degrees C is this many grams per milliliter solution. So what is the KSP of lead sulfate? Now I will tell you, I'm going to draw out an equation and kind of make an ICE table for it. It's not anything that you need to do to solve this problem, but it's going to maybe provide a conceptual framework for us to talk from. So again, we've got lead sulfate that dissociates into lead ions and sulfate ions. If we think about what's going on here, again, solids are not going to be part of our equilibrium. We're assuming that there's no other sources of lead or sulfate. We're going to have this break apart into lead and sulfate ions. And so what we're really saying is that this X is equal to the concentration of lead ions at equilibrium, and that's also equal to the concentration of sulfate ions at equilibrium. Well, one of the things I want to make sure that we define is kind of what this number is, right? So we'll get to that in just a second. Let's finish KSP here. Lead, sulfate, and for this problem, this is the unknown. We want to know what is the KSP of that, so that's what we want to solve. So the only piece of information that they give us is that they say the solubility of lead is equal to 4.23 times 10 to minus third. And what we can really think of this as being is that solubility is telling us what X is. Okay, so that solubility is telling us what X is. But we need to actually take this, I should put units in here, this is grams per 100 milliliters of solution. We actually need to get this into some type of a molarity. This is not molarity. We need to get this into a molarity so that we can then put it into this and solve for KSP. All right, so 4.25 times 10 to the minus third grams of lead sulfate for every 100 milliliters of solution. We want it in molarity. We need to have moles per liter. So we're going to have 1,000 milliliters in 1 liter. And again, that allows us to get to grams per liter. We need moles per liter. So we need to convert grams of lead sulfate to 1 mole of lead sulfate. And so that equals 1.4 times 10 to the minus fourth molar. And so again, this would be what we call the molar solubility of lead sulfate. So again, what this really means is this is 1.40 times 10 to the minus fourth moles of PbSO4 per liter of solution. What I'm going to show you is that we need to get the concentration of lead ions in solution. Right now is we have the concentration of the moles of lead sulfate. So we need to just do a little conversion here and make sure that we understand that if we wanted to convert moles of lead sulfate to moles of lead, we need to use the fact that for every 1 mole of lead sulfate, we have 1 mole of lead. Now for this problem mathematically, it's not going to matter. But when we do part B, you'll see that it does, which is why I want to make sure we understand that this is a necessary step in this problem. Mathematically, it won't change the answer, but we'll see for the next problem, mathematically, it will. So the concentration of lead 2 plus is going to be equal to 1.40 times 10 to the minus 4th. Do the same thing over here, now using 1 mole of lead sulfate makes 1 mole of sulfate. Again, mathematically, it's not going to change the value, but we get the concentration of sulfate to be equal to 1.40 times 10 to the minus 4. Now that we have these two values, we can take them, put them back up here, and solve for our KSP. So our KSP is going to be equal to 1.4 times 1.4. KSP is going to be equal to 1.96 times 10 to the minus 8th. Pretty straightforward problem here because our stoichiometry was 1 to 1 to 1. So what we'll see in our next problem is that our stoichiometry is not going to be 1 to 1 to 1, and so this kind of a thought is going to become important. I'm going to just flip to a new piece of paper to work through part B and give me a little bit more room. So let's think about what we have here. Talking about a lead fluoride solution. Again, we're taking lead fluoride, shaking it, putting a chunk of it in, shaking it up with pure water. Solubility is found to be 0.64 grams per liter. Again, calculate the KSP. So let's write an equation down for what we have for lead fluoride. So PbF2 makes Pb2 plus ions in solution and 2 F minus ions in solution. So in this problem, KSP is going to be equal to lead concentration times fluoride concentration squared. If we were to make a little ice table to kind of think about this conceptually, we'd get X and 2X. So X again being our molar solubility. X is equal to, in this problem, 0.64 grams per liter. That's information again just to show you. The solubility is found to be 0.64 grams per liter. So they tell us that. So X is equal to 0.64 grams of PbF2 per liter. So just like we did with the previous problem, we need to convert this into a molarity. That molarity will be directly equal to this guy, and twice of it will be equal to the molarity of fluoride. So 0.64 grams of lead fluoride per liter. We can get to molarity of lead fluoride using the molecular weight of lead fluoride here. Sorry, I have to look up my numbers here. 245.2 grams of lead fluoride. So that will equal 2.6 times 10 to the third moles of PbF2 per liter. And again, since we've defined this as the molar solubility, that's equal to X. So that actually is going to be the equilibrium concentration of lead. And the equilibrium concentration of fluoride is going to be twice that. And that's going to be 5.2 times 10 to the minus third. So to figure out what our K is, we're going to take the concentration of lead times the concentration of fluoride squared. So 2.6 times 10 to the minus third, 5.2 times 10 to the minus third, that quantity squared. For this problem, KSP is equal to 7.0 times 10 to the minus 8th. So, in the first part, kind of what we made sure to do was think about kind of doing this type of a dimensional analysis to convert the molar solubility, which we defined as X, into an actual solubility of each of the ions. So if you understand that when we talk about the solubility of a certain ionic substance, we're really defining that as equal to X. So again, that's why this problem, we could just use that number directly. In our next problem, we had X's and 2X's that we had here. So once we converted this into a molar solubility, which is equal to X, it was that number directly for the lead concentration, but twice that for the fluoride concentration. And one of the things just to point out that's important from this problem to think about is the approach is that we're thinking about putting a chunk of something in solution and asking how much could it break apart. So in that case, there's going to be a 2-to-1 relationship between these concentrations, and there's going to be a 1-to-1 relationship with these concentrations. And that's going to be the case if you take a solid chunk of something and throw it into solution and let that solid chunk break apart into its ions. And as we'll see in a little bit, that's going to be different than if you were to take, for example, 2 solutions that have those ions already in them and then mix them together. In that case, we're not going to necessarily have those ions present in a 2-to-1 or, in this case again, a 1-to-1 relationship. So just want to make sure that everybody understands that, every solution of lead fluoride doesn't have to have a 2-to-1 relationship between the ions. But again, this is one of these type 1 problems. We used the molar solubility, which is defined as X. We used that to figure out what the concentrations of each of the ions were at equilibrium, put them into a KSP expression, and solved for KSP.